Okay, so suppose we need to estimate the mean of something, and I have a large enough sample so that I can assume that my estimator theta hat is approximately normal theta hat like that. Okay, this was all four cases in the point estimator part. All of those were means of some sort. And yes, so here I'm assuming that theta hat, that n is large enough, so theta hat is normal, it's unbiased. And if you remember all of those, this standard error of the estimator goes low as n gets big. So what we want to be able to do is to be given or make decisions based on the following statement. So let's call this a requirement for our test. Suppose we want to say the probability that the error of estimation, theta hat minus theta, is less than b is equal to or greater than or equal to 1 minus alpha. Okay, this confidence level, and b is a bound on the error of estimation. So this is 1 minus alpha. This would give a 1 minus alpha confidence interval. We don't know, I mean, ahead of time, the way we've done this till now, just computing the confidence intervals, is we're given n, right? We're given the sample and we find the confidence interval. But we can go this way too, where we want such a confidence interval. This makes a lot more sense in a way. We want to say that our estimator is within b of the parameter we're trying to estimate, and within with a certain high degree of confidence, 1 minus alpha. Notice that we need these two numbers here because theta hat being normal and theta being constant, you can never truly bound this like this with absolute certainty, but you can bound it stochastically. You can give a probability that the bound holds. Okay, so this is what we're going to look at today. We'll just do this, I think, with one simple example, probably. I also want to introduce this notation that the textbook, that Dennis Wackerly's book, uses. Other books use this too, as they use this upper tail sort of notation denoter here. So doesn't look very symmetric, does it? Or normal for that one. Say I want this point, say this is normal 0, 1, and say I want this point here that maybe makes it have 1 minus alpha area in there, and then this would be, if I split this evenly, this would be alpha over 2, this would be alpha over 2. Well, the book calls this little z alpha over 2, and then this by symmetry is minus little z alpha over 2. And just to be clear, this is given by the quantile norm function in our Qnorm. And in here I put, remember, I put the area to the left, so it's the inverse function of Pnorm. It's the inverse CDF. So here I would put 1 minus alpha over 2, not 1 minus alpha, 1 minus alpha over 2 to get, it's a 1-to-1 function, right? And will give me this value here. So the closer this number is to 1, the bigger this number can be. It's not bounded. I mean, I could put, well, practically it is, because you can't put any number really in here. It will eventually, I don't know where it cuts off, but 0.9999999 is only going to be 7 or something like that. So, but anyway, this is what this means. Okay, so so the designer of the test, or your customer, or your consultant, your consultor, will say, look, how many samples do I need to take so that this estimate for theta will be less than b with at least this probability? Okay, so for the cases in the previous lecture, the point estimators, they all sort of satisfy this large sample rule that they are sums or based on sums, linear functions of sums, so they go normal as n gets big. Okay, so there's the justification for you. And now let's do the problem. Okay, so I think this should go pretty fast. We're just going to do this by an example. And remember, there were several types of these estimators, but we'll just focus on one. We're just going to do a single example and see if we can figure it out. Learn it from that. Okay, so suppose we have a sample y1, y2. Let's just put ... because we're going to decide how many n we need to take, where yi is the number of days hunting by license I. Really, I mean hunter with license I. So I have hunters, they're licensed hunters, and I want a measure of the average number of days that hunter spends hunting during, say, a particular year, not some random time period, but during a fixed time period during, say, the 22-23 season, winter season. Okay. All right. Okay. So what would I use to estimate this? We would use, say, let's call EYI equal mu. It's unknown. This is what we're trying to estimate. And suppose we're given, suppose the standard deviation, or say the variance of yi is equal to 100. We'll also suppose IID. These are not dependent random variables, but they're independent or close enough. Now, the yi's are not normal, but there's justification that the estimator for mu is normal because it is a large average. So mu hat will be just y bar. And this approximately is normal with mean mu and standard error. Let's write it. Let's just write it like this because we always write the normal like this. And sigma y squared, take the square root of it, we get the standard error. This is the square root of this variance, which is sigma over square root of n, right? Right, this here is and then I take the square root to get the standard error. Sorry, this should be y bar. There we go. All right. Okay, and sigma is given to be 10. Maybe this comes from several past hunting seasons by taking the sample variances. So this is not altogether a ridiculous thing to do. It's just to make an estimate for one of these so you can make some progress on maybe the thing you care the most about, such as the mean. Now, what do we want? We have not been given the direction yet, right? So, so let's say find n, find a minimal n. Let's call this A. Find min n so that the probability that y bar minus mu is less than 2 is, say, equal to 0.95. So I want my estimate y bar to be within 2 of the actual expected number of days hunting with a 95% probability. How big do I need to take n? What's the smallest n that would guarantee this statement is met? Okay. All right. Well, should be able to do this now. Been talking long enough. So what does this say? This is equal to. So let's write probability y bar minus mu less than 2 is equal to the probability. Let's divide by its standard error. So y bar minus mu over sigma y bar, which is just divide by this, right? So this is just equal to standard normal, right? Y bar minus mu over 10 times square root of n, normal 0, 1. Okay, it's the probability that this is less than, well, I have to divide both sides by this, right? So this is less than 2 square root of n over 10. And we want this to be equal to 0.95. Okay, well, notice this is 1 minus alpha, right? And notice that this means that this is z alpha over 2, right? Because I can come out this much on each side, and then I'll be right here. So we want, square root of n over 5 to be greater than or equal to, or say equal to, z 0.025. This is Qnorm 0.975, which is equal to 1.96. And let's see. Yes. So if I multiply both sides by 5, I get square root of n should be equal to, multiplying by 5, I get 9.8, or where I think this gives me 96 point something, but I will take the next biggest one because n should be an integer, and technically 96 would not quite do it. Okay, so I need 97 of those. I need to poll 97 of those licensed hunters, and the issue on whether I can trust the data, or, whether it's really independent, those are other concerns. But at least to now we have a baseline if we can make those assumptions. Let's just do another one. So this will tell me, so if I pull 97 and use the sample mean, I will be within 2 of the average of the true mean number of days that all the hunters hunt, with probability 95%. So whatever y bar comes out to be, I can say that my confidence interval, my 95% confidence interval, be y bar plus or minus 2. Okay, but I need n to be 97 or bigger, and I'll have that. Okay, find n. Let's just repeat this with different numbers. Say we think that's too big. Find n. So say the probability that y bar minus mu is, say, within 1, is less than 1, and say this is equal to 0.99. So I want a really good confidence interval here. All right, well then this will give me information about this, but I haven't made it normal yet, right? I haven't made this normal yet. So I need to divide by, so the standard error again, right? So this is equal to, just divide both sides by the standard error. Let's sort of dispense with all the writing. So this is the probability Z normal 0, 1. I've divided by the standard error is less than, the standard error was 10 over root n. I'm dividing that, so I have root n over 10. And we want this to equal Z. I have to split this, right? So I need Z 0.005, and this will equal 0.99. Okay, well, if you type in Z 0.005, if you type in Qnorm, I should put in 0.995 here, and I get 2.58 something or 57 something. Let's put 58 for this, right? So we need this. We want this. So we have square root of n over 10 should be equal to 2.58, or n equals 664. All right, so if I want this really good confidence interval, I have to order more than 6 times more data. It makes sense. That's the way you should think. Data costs money, n is bigger, costs more, you get better information, more precise information. Okay, well, the other ones are the same. The other point finding n for certain confidence intervals based on the other estimators from the point estimator section, all sort of the same. They all have standard errors that have n in the denominator, or square root of n in the denominator, and that can be made precise. You can meet any constraint more or less by choosing n big enough, and this is how you do it. Okay, thank you.